This chart tracks historical rice yields in Sri Lanka. For decades, the data shows stability, but in 2017, the trend collapses. National production plummeted by 40%. Plotted alongside producer price, the correlation is immediate. As yield shrinks, price doubles, triggering an economic shock. A 40% drop in a staple crop meant hundreds of thousands faced sudden food insecurity. The severity of the crisis required international economic intervention to stabilize the national food supply. To address disasters of this scale, the United Nations established the Loss and Damage Mechanism. This global financial vehicle is designed to directly compensate vulnerable nations when severe climate impacts exceed their structural capacity to adapt. But triggering that compensation involves a significant evidentiary burden. A country must provide strict mathematical proof that the disaster was driven by anthropogenic activity rather than natural atmospheric variance. International climate compensation cannot operate on assumptions. Validating these claims requires isolating human-induced climate variables from the ambient noise of natural weather. This requirement for proof is the basis of impact attribution, the data science framework used to quantify climate causality. Historical weather records alone are insufficient for this task. Observational data confirms that an extreme event occurred, but it cannot mathematically separate human influence from natural climate cycles. To isolate the human variable, scientists employ counterfactual modeling. They simulate a parallel Earth operating at pre-industrial carbon dioxide levels. This is then contrasted with a factual simulation. That model incorporates modern greenhouse gas concentrations, historical aerosol burdens, and observed sea surface temperatures. By comparing these two simulated realities, scientists measure the difference in outcomes. This computational method identifies the specific yield penalty that can be attributed to industrialization. The computational engine driving these comparative simulations is the D4 PDF dataset. The methodology starts with a shared historical baseline that splits into two distinct climate pathways, the factual present and the non-warming counterfactual. To provide statistical significance, each of these pathways spawns 100 individual ensemble members. These members represent slight variations in sea surface temperatures. This spread allows the models to account for the inherent uncertainties in atmospheric observations. Once generated, this simulated climate data is used as input for three distinct crop models: Desisat, APSUM, and SIGMA. These are process-based systems. They rely on static genetic coefficients, such as a plant-specific development rate, and soil hydrologic parameters to predict growth under different weather conditions. Using a multi-model ensemble approach helps eliminate the algorithmic bias of any single program, focusing the analysis on the underlying climate signal. When analyzing the long-term baseline period from 1981 to 2019, the three models show a clear, unified trend. This visualization plots probability density for all three models. Over 4 decades, every curve shifts left relative to the counterfactual baseline. This shows anthropogenic warming consistently decreased average rice yields in Sri Lanka. The impact ranges from -0.20 to -4.99. When isolating data for the 2017 harvest season, consensus disappears and the three models sharply diverge. Sigma and APSM estimated climate change actually mitigated the yield reduction during the drought. Compare that to DSAT, which calculated a severe negative impact of 7.36%. This divergence exposes the structural uncertainty inherent in these models. The equations begin to fracture when attempting to process highly nonlinear climate anomalies. Process models rely on rigid thresholds for soil water and plant stress. During periods of extreme deficits, those static parameters fail to capture the cascading physiological collapse of the crop. Averaging these conflicting results into an ensemble renders future projections for similar extreme events statistically inconclusive. This represents a critical bottleneck. Its standard process models fracture during extreme events that trigger loss and damage claims. The international financial mechanism lacks the necessary proof to act. Traditional attribution cannot process vast parameter spaces during sudden shocks. When climate conditions deviate from the norm, the rigid structural grid of these models buckles. Moving beyond these fixed equations requires a computational shift towards systems designed to detect and process nonlinear relationships within complex datasets. International climate negotiations are actively prioritizing these technological interventions to resolve the discrepancies that currently stall attribution research. Resolving the structural uncertainties that currently paralyze global climate policy requires a shift toward computational frameworks capable of handling high-dimensional anomalies. This architectural shift replaces rigid, static input nodes with dynamic, multi-layered machine learning algorithms that can ingest continuous data streams. Instead of a few fixed variables, these networks can synthesize trillions of data points, integrating satellite imagery, IoT soil sensors, and localized methane tracking. When applied to the 100-member D4 PDF ensembles, these algorithms parse the variations more effectively than traditional models, successfully mapping the nonlinear dynamics of extreme events. This creates a data pipeline that bridges the scale between atmospheric physics and the economic reality of a localized harvest collapse. Transitioning to AI-integrated data synthesis addresses the specific failures of current models during climate anomalies. By resolving these structural uncertainties, scientists can provide the definitive evidence required to move international loss and damage compensation forward.